Hello. In this video, we're going to look at mechanical and electrical vibrations. So an application of second-order linear equations with constant coefficients is mechanical and electrical oscillation problems. All right, so this includes problems like a mass on a vibrating spring, torsional oscillations of a shaft with a flywheel, flow of electrical current in a simple series circuit, and others. All of those problems can actually be transformed into a second-order linear equation with constant coefficients. Okay, so what we're going to look at is we're going to look at applications or an application of second-order linear equations. So all of those problems can all be turned into AY double prime plus BY prime plus CY equals G of T, where Y of 0 equals Y naught, where you have initial conditions as well. Y prime of 0 equals Y naught prime. Okay, so those are all applications that we can use to apply the information that we learned in this chapter. The one that we're going to look at is we're going to look at the mass on a spring. So this is like a foundational one, and so we're going to start there. So if you're going to start with a mass on a spring, well, you got to put a mass on a spring. All right, so suppose we put a mass on a spring, what would happen? So to start off with, we have our spring. And you could consider this to be the rest position. So it's L units, lowercase l units long. We go ahead and we put the mass on it, and it stretches out, right? And the additional stretch we could call capital L. So that's the elongation of the spring. We can go ahead and label this. This is the mass. And let's just note that's the mass causes an elongation of capital L. if we were to go through and represent this with a force diagram, right? So this meaning this case, once the mass is on a spring, what would it look like? So pulling downward, of course, would be gravity. And so that's going to be the mass times the gravitational constant. So that gives us our force due to gravity. And acting opposite that, right? So the object, the mass doesn't just keep falling, instead it's held in place. So that must mean that there is a counterbalancing force from the spring. And the countervailing force from the spring is governed by Hooke's law, which tells us how much force the spring takes to stretch. And the force is proportional to the elongation. So we get K times L. And so since these are since the object is not moving, these are going to be in balance. And so we can go through and we can say that mg minus KL equals 0. Okay, and so one thing about this that you may notice here is that the mg is positive and the KL is the negative, the way that we've created this. We're going to use downward as positive and upward as negative. It doesn't matter which one, which you decide to have positive and negative, as long as you're consistent. Okay, so this is the starting situation. We go through and we put the mass on a spring and then we just stop. All right, so this is not moving. Everything is in balance. So after that, so obviously we are interested in something a little bit more complicated problem than that. What we're then going to do is we're going to take the mass and we're going to put it into motion. So we're going to get it moving. So it's going to move up or down, depending upon how we set that up. And so let's do that next. Okay, so if we're going to do that, then we need to denote the position. So we're going to define the position is U of t, and it is defined relative to equilibrium. So what does that mean? So we're going to say that the equilibrium position is the position from the previous page, right, from the previous slide. So we're going to say that this position here is the equilibrium position. Okay, so starting with that, we're going to go ahead and we have our mass. Oop, hold on, let's try a little bit crazier, less crazy mass. That. All right, so all right, so recall that this is L plus capital L, distance. All right, and then we're going to apply some additional motion. So it's going to stretch even a little further. And so that additional motion, this is U of t. That's going to change over time. That's, of course, what the t stands for. And it's measured against this equilibrium position. So when U of t is 0, it will be at this spot, right? So this here, you could think of, if you draw a line here, this is the equilibrium position. And the Of course, if it moved up above equilibrium, then it would compress the spring. All right, so you could have below the equilibrium stretching the spring and against above equilibrium compressing the spring. And the spring constant works, applies in, is flexible and applies in both directions. Like, it pulls back against stretching the spring and it pushes back against compressing the spring, again with the force that is proportional to the elongation or the compression. All right, so that's it for that slide. Once we have the mass on the spring moving, at that point we can go through and we can talk about laws of motion. So Newton's second law tells us that the mass times the acceleration of an object is equal to the net force acting on that object. All right, so here we have mass times acceleration. We're using the second derivative of position for acceleration is equal to the net force. All right, so just to be clear about this, right? So when we go through and use Newton's second law here, so when we have mass times acceleration, that's the left-hand side doesn't change here. What we're going to do is we're going to fill in the net forces that are acting on it. All right, so we have mass times acceleration is given, and then that equals whatever forces are acting on it, and we still need to figure out what those forces are. So what forces are acting on the object? So first, what forces are acting on it? The first one is the force from gravity, right? Pulling the mass downward. So we can denote that, we've already denoted that. That's a Fg equals mg. And second, we have the spring force, right? The force that the spring pushes back against, or I guess pulls back against being elongated and pushes back against being compressed. And so that's going to equal K times L plus U. And we're making that negative, so because upward is negative. So L plus U, as you notice that I changed this, right? So on a previous slide we had KL. Well, that's because there is additional elongation, right? So you have, here's the base position, and it was lowercase l, and then we had that, and we just, hold on, I'll just go back to a little more. All right. So here's your base spring, and you pull it down L, and the spring pulls back against being pulled down L. And so L is just the elongation here at equilibrium. But if we put the object into motion, then you're going to have capital L plus the additional U of t is going to be the amount of the elongation. And so we have our spring constant times L plus U, and it's negative because it's acting upward. And then we're going to introduce something that we haven't discussed so far, and that's a damping force. So damping force would be the medium in which the spring is moving. So that could be open air. In open air, there is a damping effect, right? It could be in a vacuum. If there's in a vacuum, then the damping force would be 0. It could be in a liquid, which would be a stronger damping force. So it's going to act to push back against motion. So it's has a damping effect. The damping force has a damping effect. Very surprising. All right, and what is that? That is going to be the damping force. The way that it works is that it applies a force that's opposite motion. So motion is a velocity. So we have a damping constant times the velocity. Okay, and then in order to get the sign right, we're going to go through and make that negative, right? So what that means is that if the object is moving downward, right? So downward is the positive direction. So the damping acts opposite the direction of motion. So if you have a downward moving, object, then you're going to have a positive velocity because positive is downward. And so you'd want to have a negative damping force because it has to act opposite the direction of motion. So if it's moving downward, then you're going to want to have a negative effect pushing upward. If the object is pushing upward, then U prime is going to be negative because negative is upward, and then you'll get a double negative, and then it will cause the damping force to push downward instead. And so, long story short, the negative causes that you get the correct direction of the damping force. All right, and then fourth, there could be an external force. So this is where the model becomes more complicated. So the intent here is that this model is that it's simple enough that you can go through and you can construct it. But this can become the basis for a much more complicated model in that if you apply an external force like a motor, suddenly the spring on a constant starts to take on some of the characteristics of more complicated machines in terms of the different forces that are acting upon it. And so that's where the external force could make things a little bit more interesting. All right, so all of these things put together end up acting on our mass on a spring. And so let's go to the next page, actually. So we're going to have mu double prime, and then that's going to equal the net force. So what do we have? So we have mg, that's our force due to gravity, and then we have our spring force, negative k times L plus U, right? And then we have our damping force, and then we have our external force. Okay, and then we can go through and we can simplify this. This is mu double prime, get mg minus kl minus ku. That's supposed to be a u of t. Minus gamma u prime of t plus f of t. And then what do we know about mj minus kl? Mg minus kl is equal to 0. So this is 0. And then we can take these other terms and we can move them over to the left-hand side, and we get mu double prime of t plus gamma u prime of t plus k u of t equals f of t. Now the mass constant, the damping constant doesn't change, it's a constant. The spring constant is also a constant for a reason. It depends upon the spring, but it doesn't change over time. Well, maybe it would change actually, but we're assuming that the spring does not wear out or get stretched out over time. And so this structure here is a second order differential equation. It's linear and it has constant coefficients. And then from there, we could go through and add some initial conditions. So the we take U in at position 0, we call that U naught. So that could be the amount of initial displacement from equilibrium. So if you pulled the spring down, if you pulled the mass down and then let it go or pushed it up. Okay, and then U prime of 0 could equal V0. This is the initial velocity, right? So you could take the spring and it could start at equilibrium and you could push it upward or you could pull it downward just as the system is starting, and so you could have an initial motion on the mass. Okay, so let's go ahead and try applying this to a real world problem and see if we could go through and use, what we've put together so far to go through and solve it. So suppose we have a mass weighing 4 pounds, stretches a spring, two inches. Suppose the mass is given an additional 6-inch downward displacement. Then released. So you pull it down and you let it go. Okay. The mass is in a medium. That exerts a viscous resistance of 6 pounds when the velocity is 3 feet per second. So what we want to do is create the initial value problem for this situation. Okay, so to do that, what we need to do is we need to go through and find the mass, the damping constant, the spring and the spring constant. There is no external force in this case. An external force would be like an external, motor that's applied to the object. So how do we do that? So we need to go through and find the mass. So is the mass given? So these are the types of questions you need to ask. So 1, what is the mass? Let's just write down some questions. What is the mass? Is the mass 4 pounds? No. All right. So, when it comes to going through and using these American units, I can't remember what they're technically called, but when it comes to using these pound-inch units, well, I guess they're British units too, aren't they? Anyway, they're not. They're non-SI units. When it comes to using those, notice even the way that it's phrased, a mass weighing 4 pounds. So the 4 pounds is a force. All right. So what you need to do is you need to go through and start off with force equals mass times the acceleration due to gravity. Okay, so weight is a force due to gravity. And so what you need to do is you need to do 4 pounds equals the mass times the gravitational constant, which in the foot-pound universe is 32 feet per second squared. And then we can go through and solve for the mass. So you get 4 over 32 equals the mass. And then so 1/8 equals the mass. All right, 2. So once you've done that, what is the damping constant? Is that given? So some problems, they'll just tell you the damping constant is blank. Did they do that here? The mass is in a medium that exerts a viscous resistance of 6 pounds when the velocity is 3 feet per second. No, they did not. Oh, so we've got 6 pounds again. That's a force. So we have another force. And what do we know about the force is that for damping, the force is equal to the spring constant, or sorry, the damping constant times the velocity. All right, and so it tells us that the force is going to be 6 pounds when the velocity is 3 feet per second squared. And we're just going to do away with the units here. And so if you just divide this, you get 2 equals the damping constant. All right, 3. What is the spring constant? Did they give it to us? If we go back and read the problem, no, they did not. What they did tell us is that a mass weighing 4 pounds stretches a spring by 2 inches. So we haven't used that yet. That the stretching is the part of the problem that you want to go through and find for finding the spring constant. So that's the key. And so what do we know about the spring constant? We know that force equals the spring constant times elongation. And so the object that you're putting on it is going to be the force from that object is going to be what we're going to use there. So the 4 pounds is the weight. That's the amount of pull. That's the force that's being attached to the spring. And then that's going to equal the spring constant, which is we're trying to find, times the elongation. So how much elongation did we get? So it elongated the spring by 2 inches. So you want to be consistent here since we used feet per second squared, over here on this problem. And we also, although we didn't label it, we used feet per second here. So you do want to use feet for your elongation. So 2 inches is going to be 1/6 of a foot. And so we're going to get K equals 24 for the spring constant. And then 4, there is no external force. So you can just write that if you want, no external force. Putting that all together, actually, let's just do that on the next page. Putting that all together, we get 1/8 u double prime plus 2u prime plus 24u equals 0. And then our initial conditions. So if we go back, what was our initial condition? So suppose the mass is given an additional 6 inches downward displacement and then released. So there is an initial displacement. It's 6 inches downward. So again, changing 6 inches into feet, we get 1/2 of a foot downward, and downward is positive, so it's 1/2. It's positive. And then the object, we're told that it's released, so there is no initial velocity. So it's not pushed downward or pushed upward before, as you release. So that would be 0. Okay, so putting that all together, we end up with this model. And so that's how you can go through and translate a given problem, a described problem, into a model that we could actually solve. So we could go through and solve this. Now it's just a second order differential equation, um, linear, a linear second order differential equation. So this one's homogeneous, so we could go through and use our techniques from earlier in the chapter to solve it. Okay, so we're not going to do that right now. Instead, what we're going to do is we're going to move on. So these mass on a spring problems, they break down into a few different situations. And so we want to go through and examine each one of those situations to just kind of explore them, make sure that we understand them in detail, and then so that we could go through and apply that understanding when we're actually going through and solving problems. So what type of situations can you encounter the mass on a spring? Well, they break down into two major ones, and then some of them, the second one has some minor situations. But what we're going to first look at is undamped, what's called undamped free vibration. So undamped free vibration, if you just by reading it, you can maybe gather that there's no damping. And the free vibration just means that there is no external force. So you don't have an external motor attached to your mass on a spring that is pushing it. If we take that into consideration, then our problem becomes mu, our problem simplifies into mu double prime plus ku equals 0. All right, so what we want to do is we want to explore the solutions to this and see what effects that would have on the mass on a spring. So we can do that by going through and solving this. All right, so if we do that, we're going to get, to solve it, we're going to form the characteristic equation. And then we'll get and finally, we're going to get plus or minus square root of k over m I. Okay, so in solving the problem, we ended up with imaginary solution. And so we want to go through and use the appropriate situation for that. And so if we take our result and plug it in, we're going to get a cosine square root k over mt plus b sine square root k over mt. So the motion of our mass on a spring is going to be governed by this, this cosine and sine. All right, so this is where things are going to get a little bit strange. So what we can do here is that, assuming we have some initial conditions, you can use the initial conditions to solve for A and B. But we don't stop there, right? Because trying to go through and interpret how this behaves is not easy to do. It'd be complicated, right? So you have, if you were to think about it, how does the mass on a spring behave? Well, if you look at this, you'd say, well, it depends upon what A and B are and how those two things would combine, the cosines and sines. Well, what we can do, there's something cool that we can do, is we can go through and actually get rid of one of these trig functions by doing some interesting manipulation. All right, so what we can do is we can go through and we're going to let A equal R cosine delta, and then we're going to let B equal R sine delta, and then if you go through and combine this, so we have sine squared delta plus cosine squared delta equals 1. And we get, so what is sine? Sine is going to be b over r. So we're going to get b squared over r squared. What is cosine? Cosine would equal a over r. So we're going to get a squared over r squared equals 1. And then this becomes a squared plus b squared equals r squared. All right, so by going through and letting a equal this r cosine delta and b equals r sine delta, it actually enables us to create a formula where if we had a and b, we could figure out what r is. And you're like, why would we do this? It'll come together. It'll come together. Just got to be patient with it. All right, so the second thing that we can go through and do is if we have this, right, then we can go through and say, you know, cosine delta is a over r, sine delta is b over r. And so putting those together, we could go through and say that tangent of delta, which is sine over cosine, is going to be b over r divided by a over r. Then the r's cancel, so we'll get b over a. And so using this, we can go through, using this equation, we can go through and given a and b, you could solve for delta. So this substitution that, you know, we've created, and just to be clear here, at this point, this has nothing to do with anything. It just comes out of nowhere. This substitution, if we were to do it, we could go through and figure out how to find the r and find the delta and translate a and b into this r and delta, right? So instead of having the a and instead of having b, we could have r and delta. Okay, why would we do that? Well, if you go through and actually plug in these substitutions into our previous solution, magic happens. Math magic. So we have u of t equals a cosine square root k over mt, b sine square root k over mt. And now we're just going to take this thing that comes out of nowhere and we're going to say, you know what, we're going to put r cosine delta where the a is. All right, so a, r cosine delta, the rest is the same. And where the b is, we're going to put r sine delta. Okay, and now if you're well versed in your trig identities, which probably most people are not, but maybe somebody possibly watching this could look at that and be like, oh, I have it. So what we've got here is that if you factor out the r, right, so the r is not there. Actually, let's just go ahead and do that. So if you factor out the r, so we get this. If nothing else, you need to kind of delay the magic. You got to delay the payoff for just a moment. All right, this thing here, this is a trig identity, and it's the difference equation for, or the difference identity for cosine. So you can rewrite this. This is cosine of square root k over mt minus delta. Okay, and so we've gone through and found a way. This is the solution that we had on the previous page. This was the solution to our problem. We solved the problem, then went through and, you know, used the appropriate situation. You know, how do you handle complex conjugates? You go through and you know, when in the, how do you handle complex conjugates as solutions to the characteristic equation? You form them into this solution. We learned that earlier in an earlier video from this chapter. And then, so that once we have this situation, by going through and doing this, we can actually manipulate it into this form instead. Why is this form better? A lot of reasons. This form, very difficult to interpret what's happening. It's hard to look at this and be able to say anything definitive because you have a combination of two trig functions. So it's the combination of two waves, if you would prefer. So you've got a wave, another wave, and you're combining those two waves. That's going to be your solution. So this goes through and actually translates the two waves into a single wave, because it turns out when you combine these two, you get a single wave. And being able to go through and interpret how a single wave behaves is obviously much simpler than trying to interpret how a combination of two waves behaves. All right, so for one thing, just going through and recalling, what we learned in a previous courses, from like a trig course that you've taken at one point or another, you learned how to go through and apply translations to trig functions. So in this case, what we can do is we can just read off of this that the amplitude of the wave is R. All right, so just immediately you can just tell that as soon as you look at it. The size of the wave is going to be the number that you multiply by the trig function. Also, let's go through and do this. What else can we learn here? So the frequency is going of the wave is going to be the coefficient here on the t. So we get square root k over m. Then the period of the wave is going to be 2 pi divided by the frequency. And then finally, this other thing that's subtracted here, that's called the phase shift. So that's our delta. And so by going through and translating this from A and B into R and delta, we can go through and we can basically make a bunch of observations about how the object moves. Okay. So the last thing that we're going to do, but we're going to do an example. But the last thing that we're going to do before we do the example is we're going to make some observations about how the mass on the spring moves based upon this result. Right. So you go through, you put your mass on the spring into motion, and then it's governed by this equation. So what can we observe about this equation? Well, one thing that you can observe is that it continues forever, right? The cosine curve just oscillates forever. There's no end to it. Okay, so absent a damping force, right? So an object in a vacuum would oscillate forever. So that's interesting. All right, so that's one observation we can make, is that the motion continues forever. So no damping gets you eternal motion. What else? Well, if you look at this, the amplitude is R, the amplitude is constant. So not only does the motion continue forever, but there is no decline in the amplitude. If you pulled the mass down, set it into motion, it would move up and down the same amount forever. A couple more observations that you can make, actually, if you look at the frequency and the period, right? We can make some observations about how the mass affects the way that the object moves. All right, so as the mass increases, so if you went through and simplified this by flipping and multiplying, the mass would end up in the numerator. So increases in mass increase the period. Okay, so if you make the object, the mass, if you make the mass larger, then the waves are going to be longer. All right. What about the spring constant? So as the spring constant increases, how would that affect it? So the K is in the denominator. So as the spring constant increases, that's going to have the opposite effect. And so the period is going to decrease. So the spring constant has to do with how stiff the spring is. So if you had a stiffer spring, then you get shorter oscillations, shorter length oscillations. So those are all observations that we can make. All right, so let's go through and do a problem. Suppose we have a mass weighing 10 pounds, stretches a spring, (2 inches). If the mass is displaced an additional 2 inches, then given an upward velocity of 1 foot per second, find the position. Okay, in addition, find the period, amplitude, and the phase of motion. Okay, so if we're going to do that, just like the previous example, we want to start off. So we need to find the mass. All right, so similar to the last problem, they told us we have a mass weighing 10 pounds. So pounds is a force. So we have 10 equals the mass times 32 feet per second squared. And so we're going to get 10 over 32 equals the mass, which we can go through and actually we're just going to leave it like that. We could go through and reduce that, but we're just going to leave it. All right, 2. We need to find the spring constant. All right, so the spring constant, we get the force that's pulling on the spring. Well, what's the force that's being pulled on the spring? Well, that's going to be the 10-pound mass, the mass weighing 10 pounds, I should say. So we're going to have 10, and then that's going to equal the spring constant times how much does it stretch the spring, right? So it's the elongation. That's going to be 2 inches. So we're going to get 2 inches translated into feet. That's going to be 1/6. And so we get K equals 60. Okay, so that's it. We don't need to go through, there is no external force and we don't have any damping. So if you just take those two solutions, put them together, you get 10 over 32 U double prime plus 60 U equals 0. So if we go through and clear out these fractions, what you're going to get is you're going to get U double prime plus 192U equals 0. And then we could form the characteristic equation. We get R squared plus 192 equals 0. That gives us R equals plus or minus the square root of 192I, which we can reduce to plus or minus 8√3I. And so at that point, we have U equals A cosine 8√3t plus B sine 8√3t. And then the next thing, oh, whoops, and almost forgot here. So we also need the initial conditions. So U of 0, what is the initial condition? So if the mass is displaced an additional 2 inches, so an additional 2 inches would be 1/6. And then U prime, it's given an upward initial velocity. So that's going to be a negative value. So we're going to have -1. All right, so we want to go through and use those to solve for this. So let's see, can we squeeze this in on this page? If we go through and do U of 0, what would happen here? So sine of 0, 0, so it's going to kill this term. Cosine of 0 is 1, so we're just going to get A. So we'll have 1/6 equals A. And then if you plug that in, you're going to have U equals 1/6 cosine 8√3t plus B sine 8√3t. So we still need to solve for B. To do that, you could use this, our second condition. So we can find U prime. What's that going to be? So we're going to have 1/6 times 8√3, negative 8√3, sine 8√3t. And then we'll have B times 8√3 cosine 8√3t. And let's just kind of take this and move it up here. And we'll have U prime of 0. If you go through and plug in 0, so that's going to kill this sine term. And then cosine of 0 is 1, so we're going to get 8√3b. And then we know that U prime of 0 equals -1, so we'll have -1 equals 8√3b. And then B is equal to -1 over 8√3. All right, now we're going to have to go to the next page. Oh, actually, hold on. Let's do one thing before we do that. Let's take that and plug it in. So what is our final formula here? It would be U equals 1/6 cosine 8√3t minus 1 over 8√3 sine 8√3t. Now, if we had not gone through and done that manipulation with the R and delta and so on, then this would be our answer right here. That would be our final answer. That's going to be our motion. But the issue with that is that if you look at this, can you tell what the amplitude is? I certainly can't. Could you tell what the phase shift is? I certainly can't. And so we do need to go through and do some additional work on this. And technically, I mean, maybe you could guess it's, you know, using what the period and frequency is by using our previous result. But if you just told me you were combining two trig waves and you said, what's the frequency? I would have, you know, I would have no idea what the combined frequency of motion would be, or period. So that's where that result, that cool result that we've added comes in. So let's go ahead and do that next. So to do that, to use that result, what you need to do is you need to go through and use two equations, and that's a squared plus b squared equals r squared. So that enables us to get r. And then tangent of delta equals b over a. That enables us to get delta. All right, so starting with a squared plus b squared. So we have a is 1/6, so we're going to get 1/36. And b is 1 over 8 root 3. So that's going to be, if you square that, it's going to be 1 over 192 equals r squared. And so we get common denominators here. You get 19 over 576 is r squared. And then r equals the square root of 19 over 576. And that simplifies into 0.18162 is approximately r. And then you can go through and use tangent of delta. And so we have b is negative 1 over 8 root 3. A is 1/6. So this simplifies into negative 3 over 4 root 3. And then you could even simplify it further. This is root 3 over 3. So this is, you know, negative root 3 over 4. And plug that into a calculator. And you should get delta equals negative 0.40864. Putting those together, we end up with u equals 0.1862. Oops, forgot a 1 there. Cosine 8 root 3t, and then minus our shift here, that's going to be plus 0.40864. And that ends up being our motion for our mass on a spring. And so the questions I've asked is, what's the amplitude? Here's the amplitude. What else did they ask for? Amplitude, period. So the period is going to be 2 pi over 8 root 3, which is approximately 0.453. And then the phase shift is negative 0.40864. Okay, and so that's that situation. So our first situation that we look at is all the way back here: undamped free vibration, no damping, no external force. Just taking that information, if there's no damping, no external force, plugging that into our previous model that we constructed, right, all the way back here. Here's our model. If you just take that model and you just get rid of this and get rid of this, then you end up with the no damping situation. Solve it, take your solution, use our work from earlier in this chapter to construct the, you know, the solution, the solution, the motion of the particle solution, the motion of the mass solution. then you do this weird thing where you go through and break out these R's and deltas, but it turns out to be super useful because it makes it so that we can rewrite it into a single wave. Then we can read off all this information once we have a single wave. And then we get all these observations and an example. All right, so that concludes our first situation. So we have a second situation that we're going to look at. The second situation is damped free vibration. So in this case, we just have no external force, but everything else is in play. And so if we have no external force, then that turns into mu double prime plus gamma u prime plus ku equals 0. And then we can go through and try and solve that because we're interested in how the particle is going to behave under those conditions. So we form the characteristic equation. And then since these could be anything here at this point, we can just go through and solve this generically using the quadratic formula. We get negative gamma plus or minus the square root of gamma squared minus 4mk all over 2m. Okay, so here's the problem. All right, so this R value, there's multiple possibilities for this. Okay, so R could be, if you go through and solve if M, gamma, and K could be any positive values, you could have any mass, any damping constant, any damping constants are positive, and any spring constant, any positive values in these three spots, we could get a range of possible solutions to the quadratic formula, right? We could get all of the solutions that we've discussed in previous videos. We could get 2 real solutions, we could get 1 repeated solution, and we could get complex conjugates. So there's 3 possibilities. And this case has all these possibilities that we've got to look at. All right, so the first possibility, we could have gamma squared minus 4mk greater than 0. In that case, we're going to get 2 real roots. Right, and then so thus our solution. Let's go through. I want to keep this on this page. That's going to end up. We're going to end up getting u equals a e to the r1t plus b e to the r2t. Again, this result comes from earlier in the chapter when we solved homogeneous second order linear differential equations with constant coefficients. This was our solution. So if this is not familiar, then we'll go back and watch that previous video. We could have gamma squared minus 4mk equals 0. If that were to occur, then that ends up killing this whole term and you get a repeated root. This is 2 real roots, R1 and R2. If that's the case, then you're going to get u equals a e to the, all right, so if this goes away, then the repeated root is going to be negative gamma over 2m. So we can actually just figure that out. Whereas we don't know what R1 and R2 are going to be, you can actually figure that out by plugging in this solution here and just getting rid of this piece. You're just going to get negative gamma over 2m. So we're going to have negative gamma over 2mt plus bt e to the negative gamma over 2mt. And then case 3, gamma squared minus 4mk less than 0. if we have that possibility, then we're going to have complex roots. Okay. And so that formula, we can end up, I don't know if we're going to be able to squeeze this in here. So it's going to be U equals A e to the negative gamma over 2mt cosine mu t plus be negative gamma over 2mt sine mu t, where mu equals 4km minus gamma squared to the 1/2 all over 2m. Okay, so I apologize for squeezing all this stuff in, but I'm running out of additional sheets. There's a limit to the number that you can use. And this video is just kind of covering a lot of pages. All right. Where did this come from? So if you're looking at this and you're like, wait, how did you get from this being this? All right, well, the idea behind the complex roots, if this is going to be complex roots, then this here, the gamma squared minus 4mk, that's negative, meaning that you're going to have a negative under this root. You take that negative out from under the root, it becomes an I. So this piece here, this is the imaginary part of the solution. All right, so this is going to be the imaginary root, part of the root, and then we have the real part is going to be this stuff over here, no I over here. So this is the real part. So if you go back and watch the video on handling complex solutions that are complex conjugates to the characteristic equation, you'll know that the real part ends up as the ends up as the exponent of the e. So that's why we have negative gamma over 2m. It's the negative gamma over 2m. That is coming from the real part. And then the complex part, the imaginary part, it ends up getting multiplied by t. So that's where I've put these gammas in place of the imaginary part. And then this here is just the imaginary part, where it's kind of been manipulated so that it's not a negative under the root. Instead, the negative has been taken out from under the root. If you take the negative out from under the root, you're going to get 4km minus gamma squared, and then over 2m. And so this is going to be the imaginary part without the I. And so that's what the gamma is. This is the imaginary part without the m, without the I. Okay. So those are our three possibilities. So if you have a damped free vibration problem with no external force, then there's three things that could happen in the damping scenario. You could have two real roots, you could have one repeated root, you could have complex roots, you can have three different possible solutions. Okay, so let's take a look at those and see if we could make some observations on those three possibilities. Because there is some interesting, there's an interesting pattern going on there. All right, so one thing that we can start off by saying is, since m, gamma, and k are all greater than 0, we can say that gamma squared minus, hold on, sorry. We can say that gamma squared is greater than gamma squared minus 4mk. Right? If m and k are positive, then if you take gamma and you subtract some stuff, then it's going to make, you know, you're going to end up with a smaller result. Okay, so we can go through and use that to discuss this for the first case. If gamma squared minus 4mk is greater than 0, then R1 and R2, which equal negative gamma plus or minus the square root of gamma squared minus 4mk over 2m, have to be less than 0. Why is that? So if this, so that it comes down to this right here, right? What would happen if you took the square root of both sides of this? Okay, so we would have that gamma is bigger than the square root of gamma squared minus 4mk. If gamma is bigger than the square root, then if you took negative gamma and you added it to the square root, if gamma is bigger than negative gamma plus the root, you're going to get a negative number. And clearly negative gamma minus the root, you're going to get a negative number. And so we're going to end up with negative values in the numerator in either case because of this result. So assuming these are all positive, then we can go through and say this is true. If this is true, then this is true. And that implies that the negative gamma here is going to end up being bigger than whatever we have in this spot. So it doesn't matter whether we're adding or subtracting, we're going to end up with a negative number. So it tells us that R1 and R2 are both negative. B, if gamma squared minus 4mk equals 0, then we have R equals negative gamma over 2m. C, if gamma squared minus 4mk is less than 0, then, so this was a little bit more complicated, then you're going to end up with your solutions, your complex conjugate solutions. You're going to have negative gamma over 2m plus or minus the square root of, I don't know why I drew that square root so big. It's going to be the square root of gamma squared minus 4mk over 2m. So this is the real part. And so we have a negative real part. To your complex conjugate. So you have a negative real part. So what does that mean? So we have R1 and R2 are negative in the first case. R is negative in the second case. And in the third case, we have a negative real part. So what does that mean? Why does that matter? Go back. Here's the first case. If R1 and R2 are negative, that means you have negative exponents. What happens to negative exponents as t increases? It's going to cause these terms, these exponential terms, to go to 0. In the second case, if we have negative exponents, which we've already have written in here, that's going to cause these exponential terms to go to 0 as t increases, and they will drown out that t there. And in the third case, we have negative real roots for the real part of the complex conjugate. That's going to cause these exponential terms to go to 0, which is going to drown out the cosine and the sine. So putting that all together, no matter what, we're going to have negative exponents. Oops. On the exponential term. Thus, in all three cases, so keep in mind that u is the motion of the object is based upon u. So if in all three of these cases the u goes to 0, right, because the exponential terms go to 0, then that means that the object over time has to go to 0. Right, so what does that mean? Thus, if there's damping, the object eventually stops moving. Or sorry, I should say the object eventually goes to 0. So this intuitively makes sense that if you were to go through and pull down an object and then release it, it doesn't move forever, typically, right? So that's because there's damping in the air that we live in. Certainly if you put it into water, the object would eventually stop moving up and down. And so, we can go through, and that does kind of intuitively make sense, is that we're accustomed to objects not moving forever. All right, so next we're going to take a closer look at the third scenario. So what we could do is we can go through, let's copy it over. All right, so we have u equals a e to the negative gamma over 2mt cosine mu t plus b e to the negative gamma over 2mt sine mu t, where mu equals 4km minus gamma squared to the 1/2 over 2m. Okay, so what we're going to do with this scenario C is, because we have these cosines and sines, what we want to do is we want to do the exact same thing that we did with the previous situation where we had the oscillations, and we want to go through and get this down so that we only have a single trig function, and then we can go through and make some commentary on what the motion is going to look like. So if we go through and say if A equals R cosine delta and B equals R sine delta, then you can do the exact same manipulations we did earlier, and we're just going to skip over them this time. You'll get R e to the negative gamma over 2m t cosine mu t minus delta. And so what we want to do here is we want to compare the previous result. So no damping. We get u equals R cosine root k over m t minus delta. And so if you were to go through and sketch this, so you just pick some starting spot here, but we go through and we get and the motion stays consistent with the same, well, that's supposed to be the same as that, with the same top and bottom. Meanwhile, if we have u equals R e to the negative gamma over 2m t cosine mu t minus delta, what's that going to look like? So the one difference, what's the one difference that's there? It's this exponential term with a negative exponent. So that's going to cause the waves to decrease in amplitude. So we go down, first wave looks similar, and the next wave doesn't go quite as high as that. And the next wave down doesn't go as low as that. And so you get the waves eventually go to 0. Okay, and so adding damping causes it so that when you pull the mass down and then release it, the mass eventually goes back to equilibrium. No damping, the mass continues forever. Okay, so one observation about this is that this is the scenario where we have gamma squared minus 4mk less than 0. If you go through and manipulate this, this is gamma is less than 2 root k over m. So it enables us to go through and, so this is this situation. Oh, and keep in mind, all right, so hold on, one more thing. So there's no damping here, so this is gamma equals 0. So no damping, you get this motion. If you get gamma less than 2 root k over m, which is just by moving this over and square rooting both sides, then you get this motion. Okay, so gamma 0, gamma smaller than this number. All right, what's the next scenario? We could have gamma, so the next scenario is we have gamma squared minus 4mk equals 0. So that turns into gamma equals 2 root mk, 2 root k over m. Oh, wait, hold on. That's not supposed to be k over m. It's supposed to be 2 root km. Apologies for that. All right, so smaller than 2 root km, it does this. Equal to 2 root km, we get case B, right? Which is this case here. This is case B, the repeated root. And so that's the U equals AE to the negative gamma over 2m t plus BTE negative gamma over 2m t. Right, that's our repeated root scenario. And then we finally have minus 4mk greater than 0. That converts into gamma is greater than 2 root km. And that one we get U equals AE to the R1t plus BE to the R2t. And so you can go through and you can, the point of this, what I'm trying to get at here is you can actually split these up based upon the damping. So if the damping is 0, this scenario. If the damping is less than this calculation, this is called the small damping scenario, then you get this scenario. If damping gets big enough that gamma equals 2 root km, then you get this scenario. This scenario is called critically damped. And if the damping continues to increase, then you get to this scenario, which is over damped. All right, so as damping rises, you get this different behavior. So no damping, oscillations forever. Small damping, you get oscillations, but they decrease. And then you get, as damping, you get critically and overdamped. What do these two scenarios look like? Great question. So depending upon the position of the object, you can pass through equilibrium either once or no time. So it could look like this and then goes to 0, or you could release it and it just goes straight to 0. So those are the possibilities depending upon the damping relative to, and to be clear about this, this is the damping relative to the spring and the mass. So this is giving you a formula that relates those three quantities. So that's really cool. That's a really cool result, I think. All right, and then I can get one more page out of this. All right, so we have, I guess at worst, if I run out of pages, I can go back and really erase old pages. All right, so suppose we have a situation that's given by the following values, right? So if you look at this situation, we have the mass is 1, the damping constant is 1/8, the spring constant is also 1, you've got 2 initial displacement downward, and then no initial velocity. And what you're asked to go through and do is you're asked to go through and solve this situation, and then you're asked to go through and find the frequency and the period for this wave structure, which I forgot to label on here. So the frequency is dependent upon gamma. Let's actually open up just a little bit more space over here for a little bit more in the way of notes. So this is going to be the frequency. And then if you went through and took 2 pi divided by gamma, you would end up getting the period for this wave structure. Now, so it behaves a little bit like a wave, right? But not an eternal wave. And so what these are called the quasi frequency and period. So that's the name for them if you come across that name. So the quasi frequency and the quasi period. It's kind of hard to read that. Quasi frequency and period. All right, so we're given this situation and we're told to go through and solve it and then give the quasi frequency and the quasi period. All right, so if we're going to solve this, you first form the characteristic equation. And you can clean this up to 8r squared plus r plus 8 equals 0. And then we can go through and say r is going to be -1 plus or minus the square root of 1 minus 4 times 8 times 8 divided by 2a, which is 16. And that we could simplify into -1 plus or minus the square root of -255 over 16. So it's going to be -1 plus or minus root 255 I over 16. And so from there, we have complex conjugate roots. So we can go through and say that u is going to equal a e to the -1/16 t cosine root 255 t plus b e -1/16 t sine root 255 t. Okay, and then next I'm just going to hit fast forward on this. I actually did go through and solve this whole problem, but we've already solved a similar problem to it once before. So if you go through and solve this, you're going to get a equals 2 and b equals, where is my b in my notes on here? 2 over root 255. Okay, and that's just using the initial conditions as we've done many times before in previous videos to go through and solve for a and b. So I'll go ahead and write out the next step because we've only done it once, and that is if from here you want to go through and solve for r, so that's use a squared plus b squared equals r squared. So that's going to be 4 plus 4 over 255 equals r squared. And if you go through and get common denominators here, that's going to be 1024 over 255 equals r. And square both sides, and the square root of 1024 is actually 32. So we're going to have 32 over root 255 equals r. And then after that, we can go through and find delta. So we have tangent of delta is going to equal b over a. So b is 2 over root 255 over a, which is 2. So this turns into 1 over root 255. And then if you do tan inverse, you should get delta equals 0.00109. Okay, so the last step here, so we can go through and rewrite this. So this is going to be u equals 32 over root 255 e to the negative 1/16 t cosine of root 255 t minus delta. All right, so that's our equation of motion. And then the question is, what is the quasi frequency? Ooh, whoops. This is supposed to be root 255 over 16. I forgot the 16 here. And here. Sorry about that. And so to go through and figure out what the quasi frequency is, that's going to be the square root of 255 over 16, which is approximately 0.998. And then the quasi period is going to be 2 pi divided by root 255 over 16. And that's going to be approximately 6.295. Okay. So that gives us the frequency is the number of waves in over a 2 pi period, and the period is the length of those waves. Okay, so that explains how to go through and use this this second scenario to go through and let's take one more look at it. The second scenario, assuming we had damping, we have the 3 possibilities. We discussed the possibilities, made some observations. So the damping is going to cause the object to eventually go back to equilibrium. We then looked and compared how the damping value relative to, well, if the damping is 0, you get this scenario, but then we looked at how the damping compared to the mass and the spring constant gives you these different possibilities. And then we went through and did an example that fit in with this scenario, so you could kind of explore it. And so that's it. That's the whole video. That was a long one. I wasn't timing it, but I'm almost afraid how long that one was. All right. Thank you for watching. See you next time.